Welcome to the Into AI Safety podcast, where we document my shift to a career in AI safety. This show aims to serve as a mentorship proxy for those getting into the field, and a mentorship amplifier for our guests and myself. As always, I am your host, Jacob Haynes. Alright guys, I hope you're ready for this one, because I am super excited to talk to you about a paper that dropped 5 days before recording this, Large Language Models, a Survey. Yeah, there are definitely other ones out there, but there are none that are this up to date. This one also has an all-star author list. Now, after doing a little bit of research, I found one of their LinkedIn posts that was talking about this paper, and it details what they are all currently doing. Whew, okay. I hope I don't botch any of your guys' names. We have Shervin Menei, who is an ML manager at Cambia Health Solutions, Tomas Mikolov, who is a senior researcher at Czech Institute of Informatics, Robotics, and Cybernetics, Narges Nikshad Kazmaki, a postdoc at Köln University of Applied Sciences, Meysam Asghari Chanaglu, who is a staff AI researcher at Ultimate, Richard Socher, who is the CEO at U.com, Xavier Amatrayan, VP of Engineering Product AI Strategy at LinkedIn, and Zhanfeng Gao, Distinguished Scientist and Vice President at Microsoft. First, let's talk about the things that I really liked. The visual aids that were designed specifically for this paper are really well done, and they definitely make the paper much more accessible. I actually think they're so helpful that I'm going to include many of them on the Into AI Safety podcast website, which is into-ai-safety.github.io. When you hear me talk about visuals in the paper throughout the rest of this episode, note that anything I mention will be on the website. Next is the immense list of citations. I think there's something like over 160 included in this paper. For both newcomers and experienced researchers, having a paper like this, which has such a massive list of some of the most influential and important papers in machine learning as a field, is incredibly useful. Finally, I think this is actually a pretty decent tool for someone who wants to get involved in the technical side of machine learning. More specifically, I think that if you can understand maybe 80+% of the words and concepts that are introduced in this paper, you should be able to have a meaningful conversation about machine learning with basically anyone in the field, regardless of what their expertise is. Now, things I didn't like as much. It uses terminology that, while widely used in the machine learning field, is probably not the ideal terminology to be using, although I guess I'm a culprit of this too with using AI in my title. There isn't a light version to this paper, that is, there isn't an executive summary. The graphics are able to address this somewhat, but if you don't separate them from the rest of the paper and say, look, here's the TLDR, it's not really as useful. Along similar lines, I wish they had published this as a website as well, ideally with visualizations of how ideas are related to each other. Personally, I'm a big fan of dynamic experiences, especially when it comes to making research accessible, and I think that would have been really helpful here. At the same time, I do understand the value of having this as a paper. Finally, and I'll mention this at the end as well, but security, ethics, and responsible AI is clearly an afterthought here. Before we get into the actual paper, I'm just going to give you a broad overview of how it's structured. Section 1 is Getting to LLMs. Well, that's the title I would give it. It's actually called Introduction. Section 2 is an overview of current models. Section 3 talks about how they're built, the internal structure, and the training process. Section 4 considers different ways that LLMs can be used. Section 5 is data sets for evaluation, and Section 6 are benchmarks. These are highly related. Section 7 is current challenges and future directions, and Section 8 is the conclusion. Alright, so we start with how we got to LLMs. Things started in 1950s with Claude E. Shannon at Bell Labs. This guy's master's thesis was a symbolic analysis of relay and switching circuits, which demonstrated that electrical switches could construct any logical numerical relationship. This, in turn, established theory behind both digital computing and digital circuits. During World War II, he wrote Communication Theory of Secrecy Systems, which is considered to be one of the foundational pieces of modern cryptography. And his most famous paper, A Mathematical Theory of Communication, laid the foundation for the entire field of information theory, resulting in it being called the, quote, Magna Carta of the Information Age, end quote, by Scientific American. These, of course, aren't even the work that is cited in this paper, which was titled Prediction and Entropy of Printed English. Basically, this guy was bonkers. Much later down the line, we got to statistical language models, or SLMs. These use n-gram models which predict the likelihood that a given word will follow a specific phrase of n-1 words. For example, if our context phrase is, I'm going over, such a model would assign high probability to the next word being there, leading to I'm going over there. A substantially lower probability to the next word being yonder, meaning I'm going over yonder, and practically zero probability to the next word being bananas, or I'm going over bananas. The representation of natural language data compatible with these n-gram models is very large, due to the immense size of vocabularies. Although the data take up a lot of space, when represented directly, a majority of the entries are zero. This property of having a vast majority of entries which are zero, while there are pockets or individual data points which have meaningful information, is called sparsity. Next were the neural language models, or NLMs, which leveraged the sparsity of natural language representations by creating substantially smaller representations that have a high density, called embedding vectors. Neural networks are then trained to predict the next word based on preceding embedding vectors. The first NLMs were task-specific, but soon they gave way to pre-trained language models, or PLMs, which are not designed for a single specific task. Large language models, or LLMs, primarily refer to transformer-based neural language models, although there are a few which have been very recently introduced called structured state space models, or SSMs. Alright, so how do we define what an LLM is? Well, as the name suggests, LLMs are large in size. Here, size is referring to the number of parameters within the model. It doesn't necessarily make sense, though, to have a special distinction for large language models if there isn't something else that is unique about them. The key distinction that this paper makes is that LLMs exhibit so-called emergent abilities. Specifically, the paper names in-context learning, instruction following, and multi-step reasoning. We're going to go on a tangent with emergence real quick, because I think it's really important to understand what this concept is, especially because it's an active area of study. Emergence is a concept first coined by philosopher G.H. Lewis and is a central idea to the study of complex systems. In this context, emergent phenomena are when an entity exhibits properties that its components do not have. The most intuitive examples can be observed in nature through collective behavior, such as flocking of birds, schooling of fish, and colonies of ants, bees, and termites. Emergence is also relevant in multiple other domains, such as game theory, nonlinear dynamics, and pattern formation. Based on my research, the use of emergence as a concept in machine learning can be traced to a blog post by Jacob Steinhardt on January 7th of 2022 to his blog, Bounded Regret. 6 months later, Jason Wei et al. Released a paper entitled Emergent Abilities in Large Language Models, which would then be published in Transaction on Machine Learning Research the following month. Both the blog post and the paper mention the 1972 essay More is Different by Philip Anderson. In Anderson's words, emergence is when quantitative changes in a system result in qualitative changes in behavior. Wei et al. Then explicitly define emergence in the context of large language models, stating that, quote, an ability is emergent if it is not present in smaller models, but is present in larger models, end quote. Since then, emergence as an idea has been creeping into the ML lexicon. With a recent paper, Sleeper Agents, Training Deceptive LLMs That Persist Through Safety Training by Huminger et al. At Anthropic, recognizing emergent abilities as a threat vector. At the same time, however, there have been 2 papers published that push back on this idea of emergent abilities. In April of 2023, Ryland Schaefer et al. Published the paper Are Emergent Abilities of Large Language Models a Mirage?, which makes a very compelling case that these emergent abilities are an artifact of poorly chosen metrics, rather than discontinuities in performance. The paper received one of 2 outstanding main track paper awards at NeurIPS 2023, which is known to be one of the most prestigious ML conferences. The other paper, Are Emergent Abilities of Large Language Models Just in Context Learning?, was released in September of 2023. In this paper, Shen Liu et al. Claim with a significant amount of evidence that abilities characterized as emergence can be explained through the phenomena of so-called in-context learning. To muddy the waters even more, many papers in machine learning and other fields will refer to ideas, behaviors, and properties that are emerging or that have emerged, using the word for its true definition and not a domain-specific keyword. Oftentimes, it can be very difficult to discern which is the case, as very few papers will think to define such ambiguous terms explicitly. Now, although I did bring up the other 2 papers, which provide at the very least strong basis to arguments against the ubiquity of emergent abilities in LLMs, I would also like to point out that regardless of whether or not these abilities could have been predicted prior to scaling, almost all of them were not. Tagging these abilities accordingly and paying closer attention to what we expect new models to be capable of is therefore probably a good idea. The potential that a new frontier model could exhibit seemingly unprecedented capabilities and behaviors is still true, and therefore we should not ignore this phenomenon due to finding an apparent solution. My suggestion is to think of these abilities as superficially emergent as we move forward, as I think this would strike a perfect balance between the 2 sides. Alright, dismounting my soapbox and continuing with the remainder of the paper. Section 2 then starts out with a brief overview of the early pre-trained NLMs, which are the predecessors to LLMs. Perhaps the most well-known recent milestone in the field of machine learning was the transformer architecture, first described by Vaswani et al. In the 2017 paper, Attention is All You Need. Transformers are characterized by self-attention, which allows the model to store information about the influence that each word has on other words within an input. Importantly, this architecture allows for substantially more parallelization than the previous hot architecture recurrent neural networks, or RNNs. This is relevant because it in turn allows for training of very, very large models in the same amount of time as a smaller one, provided you have enough computing power, or GPUs/TPUs. There are 3 architecture categories for these PLMs: encoder-only, decoder-only, and encoder-decoder models. The paper goes into more detail regarding differences in architecture and tasks used for training. The remainder of this section is a long list of LLMs categorized into what they call LLM families. The GPT family from OpenAI, the Llama family from Meta, and the Palm family from Google. This section reads fine and gives a pretty good intro to each various model within each LLM family. The paper also considers LLMs that do not fit into those categories at the end of the section. Notably, they bring up that the Llama family is, quote, open source, i.e. model weights are released to the research community under a non-commercial license, end quote. Wait a second. Is that really what open source is? Well, no, it wasn't. But unfortunately, it has been redefined by ML industry movers. Now, I can't get into this idea in depth during this episode, but know that I will be sharing my thoughts on this issue soon. In this section, they throw out lots of terms commonly used in ML, so it can get a bit complicated. Admittedly, I did not know the precise definition of quite a few of these phrases. While this does raise the barrier to entry for engaging with the paper, it is also a very valuable resource for determining and understanding gaps in your own knowledge. Accompanying this section are a couple of visuals, a high-level overview of popular language models, a visualization of LLM families, and a timeline of the most representative LLM frameworks at the time the paper was published. As I mentioned earlier, all of these will be included on this episode's page of the Into AI Safety podcast website. On the topic of visuals, I think that probably the best one in the entire paper accompanies the next section. It provides a very general overview of how LLMs are built in diagram form. Although the entire section is definitely worth a read, I'll just go over some of the items that stuck out to me. First, the section includes a brief description of what tokens are, and 3 of the more popular methods for turning words into tokens. I highlight this because I think that, usually, this aspect of the LLM process is not thought about as much. In addition, special attention is paid to the idea of fine-tuning, which is probably reasonable given the importance of the practice in ML. Fine-tuning is when a model that has already gone through an initial training phase, also known as a pre-trained model, is trained again on data specific to some subset of tasks. The practice allows for models to become very good at those specific tasks with much less data than was required for the initial training phase. Typically, fine-tuning will improve performance on the task and make it more likely that an arbitrary but appropriate input will result in a high-quality output. It also mentions that one of the reasons to fine-tune models is to align the outputs of a model with human expectations. It even explicitly defines AI alignment as, quote, the process of steering AI systems towards human goals, preferences, and principles, end quote. Until recently, reinforcement learning from human feedback, or RLHF, has been the standard approach for attempting to address alignment in commercial LLMs. In RLHF, a reward model is trained based on human rankings of preferred model outputs. That reward model is then used to fine-tune the base LLM further, encouraging outputs that the reward model scores higher. In May of 2023, Rafailov et al. Released a paper, Direct Preference Optimization. Your language model is secretly a reward model, to archive. The paper makes the argument that RLHF is both complex and unstable, and proposes that alternative of DPO, or Direct Preference Optimization. Additionally, just 1 week before the survey that we're talking about in this episode was published, another RLHF alternative called Kahneman-Tversky optimization, or KTO, was proposed by Ethayaraj et al. In the paper KTO, Model Alignment as Prospective Theoretic Optimization. Although I don't believe that we have really tested the limits of either of these new approaches, it is encouraging and exciting to see what is possibly the next wave of alignment techniques. Another fundamental step that all LLMs include is decoding the tokens back into human vocabularies. Although this may seem relatively straightforward, there are actually multiple different options, and the one chosen can have massive implications for model outputs. This portion on decoding also addresses how the concept of randomness, or stochasticity, is introduced as a user-defined parameter through the idea of temperature. This may, at first glance, seem like a strange abstraction to make. In other words, what does temperature have anything to do with what we're talking about? I believe that the idea was originally introduced to the field of optimization by Kirkpatrick et al. In Optimization by Simulated Annealing, an article released in the journal Science in 1983. The algorithm is inspired by the process of annealing, which is used in metallurgy and materials science. The paper finishes this section by acknowledging that LLMs have gotten incredibly expensive to train, run, store, and adapt, as well as some methods that have been designed and used to reduce these burdens. The next section is titled How LLMs Are Used and Augmented, but the authors made the choice of starting it off with a subsection on LLM limitations, which I think was an excellent choice. In this subsection, they highlight the following items. LLMs do not have state or memory inherently. There are ways to augment models to address this, with OpenAI recently announcing that ChatGPT now has the ability to recall information from other conversations. But this required additional infrastructure and workflows. It was not part of the GPT models inherently. Next, LLMs are stochastic or probabilistic. Even when temperature parameters are reduced to 0, there is still randomness inherent to their output, meaning that there will always be some variance. Their information is limited to what they were trained on, meaning that oftentimes it is not up to date. Again, this failure mode can be addressed by augmenting the model with access to external data by, for example, searching the web, but it is not part of the models by default. LLMs are, as the name would suggest, large, so most models are too big to run on device, and inference, or giving the model an input and running it, is relatively slow. Well, at least in this age, where any amount of buffering is annoying and waiting more than 10 seconds for something to load seems disruptive. Last, but certainly not least, is that LLMs, quote, hallucinate, end quote. Here, the authors explain that at the center of this so-called hallucination is the fact that LLMs, quote, do not have a notion of truth, end quote. Alright, again, this one's important, so we're going on an aside on hallucinations. As a precursor to this section, note that I verified my understanding of hallucinations as a psychological symptom with the paper Hallucinations and Related Concepts, Their Conceptual Background, which was published in the journal Frontiers in Psychology by Teles Correa et al. In 2015. Having said that, my opinions regarding the personification that this term implies are my own. Hallucinations are a highly complex symptom for a variety of psychological disorders and normal physiological traits. Not only has the concept of hallucinations resisted definition and consensus for hundreds of years, but it also has very strong implicit ties to sapience. Or in other words, simply by stating that something is hallucinating, you have implicitly associated it with human traits. While saying that you discovered a model hallucinates makes for a great title, it encourages personification of AI systems, which is widely agreed to be harmful practice for both the general public and individuals in the industry. If we, as a research community, want the technology we contribute towards to be used in a safe manner, we have to stop using sensationalistic and poorly thought out naming schemes. In short, LLMs are not hallucinating. They are generating text that was highly probable based on their training data and the context provided. You should not expect their outputs to be factually correct or wholly objective. Now, I don't want to simply be complaining about the word without suggesting an alternative, so let's think about some. The paper defines two broad categories of this phenomenon. The first, so-called intrinsic hallucinations, directly conflict with the source material, introducing factual inaccuracies or logical inconsistencies, while the second, so-called extrinsic hallucinations, do not contradict the source, but are unverifiable, encompassing speculative or unconfirmable elements. I suggest using the word fallacy as our primary replacement and defining direct fallacies to be akin to the current intrinsic hallucinations, and indirect fallacies to correspond to extrinsic hallucinations. Despite my dislike of the currently used term, having a model which could guarantee outputs containing no fallacies, direct or indirect, would be highly valuable. So there have been many methods proposed to decrease, mitigate, and understand this phenomenon. The paper takes a surface-level look into some of these methods. Following this subsection, we get into the uses of LLMs. Personally, I would have preferred the diagram of LLM capabilities to be located in this section instead of at the top of the paper, but it's not a major concern. I do think that the diagram is helpful for understanding how different tasks are related to each other. The remainder of this section is broken up into 4 parts: prompt engineering, retrieval augmented generation, or RAG, tool use, and agents. Prompt engineering refers to the practices and techniques used to create an optimal prompt to a language model such that a specific goal will be achieved. The paper specifically calls out the domain as both having a potential to revolutionize certain aspects of machine learning, and also needing to adapt traditional engineering practices such as version control and regression testing. In other words, prompt engineering seems to have a lot of potential, but we need to be systematic, deliberate, and thorough as we continue our research. The paper discusses chain of thought, or COT, tree of thought, or TOT, self-consistency, reflection, expert prompting, chains, rails, and automatic prompt engineering, or APE. Note this is the second time that a concept has used the acronym APE within this paper, the other being absolute positional embedding in a previous section. Augmenting LLMs with the ability to use external tools, typically through APIs, is discussed as well, primarily in the context of retrieval augmented generation. The core premise of RAG is to make reported information more detailed with higher accuracy. Think of an LLM that leverages RAG as one with the ability to search a database. The last subsection here considers LLM agents. In this paper, an agent, quote, is typically an autonomous entity that can perceive the environment using its sensors, make a judgment based on the state it currently is, and accordingly act based on the actions that are available to it, end quote. Agents go beyond an LLM augmented with tool use because they are designed to handle tasks that require some amount of autonomy and decision making. All right, we're almost done. Next two sections consider popular datasets and benchmarks for LLMs. The first of the two sections lists and briefly describes a wide variety of popular dataset-based evaluations, or benchmarks. These datasets are also broken up into categories based on the type of capability that they attempt to assess. A visual representation of the dataset split into these categories, a histogram of the licenses used by datasets, and a table overview of the datasets are included in the paper. It is worth noting that some of the evaluation metrics used in these datasets are very complex in and of themselves, such as BLUE, PASSET-K, Rouge, and F1 score. Furthermore, the evaluation metrics reported in the table are not necessarily the ones utilized by your go-to model evaluations platform. I know this because I have worked extensively with the Truthful QA dataset, and the Eleuther AI model evaluations harness, which is used for the well-known Hugging Face LLM leaderboard, does not use any of the methodologies outlined in the paper which accompanied the Truthful QA dataset. Now, I wouldn't expect the authors of this survey to be able to scrutinize each and every one of these tests, identifying the way that they are currently being evaluated at scale, and then make these clarifications. It would just be a ton of work for something that should be on the groups hosting the evaluation leaderboards. However, the fact that there is an inconsistency here further emphasizes the idea that researchers and model developers need to be rigorous and detail-oriented when attempting to evaluate their models. Potentially, the dataset is not being evaluated as intended, or is being compared to models that were evaluated on a different metric altogether. Along similar lines, the survey also points out that models of differing types or sizes, referring to number of parameters in the model, which also implies more training data and increased training costs, should not be compared to each other wholesale, just the same way that we don't make serious comparisons between the speaker on our phones and a multiple speaker surround sound system. To aid in understanding the differences between models, two tables are included. The first defines classifications and what they mean, while the second lists a subset of well-known models and which categories they fit into. A visualization of these categories is also included. We then get into a series of tables which compare model evaluation scores on common sense reasoning, symbolic reasoning, world knowledge, coding capability, arithmetic reasoning, and a fallacy evaluation. They call this a hallucination evaluation. This portion definitely feels necessary to include, but it is also the least interesting to me because of how they set it up. Now, if we instead had some lively plots color-coded with model families and marking their improvement on evaluations over time, that would be an entirely different story. But as is, it's just a jumble of numbers. The last section, excluding the 4-sentence conclusion, is challenges and future directions. The authors conjecture that a very recent trend of smaller, more efficient models that maintain a majority of capabilities is likely to receive more attention in the near future. Speaking of attention, we have our first indications that maybe attention is not all you need with the introduction of state space models, or SSMs, which leave behind the transformer altogether. Also mentioned are multimodal models, which can utilize multiple types of data, such as text, images, and audio. We have already seen the first multimodal models, but companies are promising the next ones. In addition, the paper highlights that as the general public begins to integrate LLMs into their everyday lives, we will see new use cases and methodologies being adopted. At the end of this portion of the paper, the authors include what I believe to be the shortest subsection in the entire paper, titled Security and Ethical Responsible AI. To me, this makes it clear that preventing misuse and ensuring responsible behavior, including the prevention of bias, is an afterthought. Overall, I really appreciate this paper for a number of reasons. One, it gives us an idea for how ML researchers view LLMs when they are given the opportunity to think about the paradigm and reflect on it. Two, it provides a sorely needed technical introduction to LLMs that is still relatively accessible. Three, absolutely immense citation list which hits basically all the notable purely technical ML papers I can think of. Note that ethics, governance, and human interaction are not included here. Alright, well, I hope you guys enjoyed me going through this paper. It definitely wasn't what I had originally envisioned this episode to be like, and probably took substantially more time than an advice-based minisode would have taken. But when I saw this paper had just been published, I thought it would be a great opportunity to publicize it as a resource. Although definitely still technical, I tried to make this episode as accessible as possible for newcomers, or even people who aren't as interested in the details of AI, but still want to know more about the technology. If you think that this episode could be helpful for anyone you know as an introduction to large language models, please share it with them. I believe that getting more people to meaningfully engage with the discussion surrounding the appropriate research and deployment of this transformative technology is critical, and I would really appreciate it if you would help me achieve this goal. Well, see you next time.